Hello students, welcome back. Let us resume our discussion in section 1. We went through 2 videos already, and let's try to speed up a little bit. In the first video, we went through the standard form, the fraction form, and these kind of example problems, 0 over 0 type and infinity over infinity type. Furthermore, we went through a problem on 0 times infinity type as well, when the transformation is rather obvious. E to the negative x power, you can easily push it downstairs and get a fraction. And then in the second video, I spent a bit too much time on these two. So I think I'd better speed up a little bit. Alright, here we go. Let's discuss these types. And let's take a little bit bigger font again. Okay, the typical technique is this. If you have a to the b power, one typical way to handle this is to take the log. And we have kind of problems like these. Another way is to use the change of base formula. This a to the b power is actually equal to exponential of b times log of a. And then if you compare the second form with the previous expression, the exponent here is the same as before. Do you recognize? This one here, same as that one. So essentially the same technique is being applied. Whether you take the log and then in the end take the exponential back, or go directly with the change of base formula, either way, you're going to end up with same type of computation right here or there. Okay, ready? Here's the first problem. Solution number 1, let's take the log. Take the log, and then this x squared comes out as coefficient. And what do you have? We have 0 times infinity type limit. Keep logarithm on top and push the power function down below, and then apply L'Hopital's rule. We went through this before. So what is this? We got 0, but that's not the answer. Log of whatever you wanted is 0, so we have to take the exponential back. That's the answer. You see, that's not the end of the problem. You have to take the exponential back. Or you can do directly with this. Change the base, e to the x squared log of x, and that part, that's the same as before. So the same computation yields same answer, e to the 0 power, which is 1. If you take solution 1, then you get this. And then forgetting about this, that's one of the common mistakes I see. Stopping here. Forgetting about the final answer. If you use the second expression here, then there's much less danger, but it looks a bit more complicated, especially over here. So there's a bit of a trade-off. Which method do you like better? My preference is the second method, but our textbook's preference is the first. Another problem here, and method number 1, take the log. 1 over x comes out, and then we have a fraction, so we can go ahead with L'Hopital's rule. That's easy, we have 0. But remember, that's not the answer. We took the log, so we have to take the exponential back. That is the answer. Many students stop here. I've seen many. That's not the answer. We need one more step. Now, if you use a change of base formula, you can avoid that pitfall, but the exponent part will become more complicated. Here, same computation as this one applies. So in the end, we get the same thing. Okay, here's another problem. Again, method number 1, take the log, and power comes out its coefficient, and this limit is more or less a trivial limit. It's not L'Hopital's rule, anything like that. As a matter of fact, you see, 1 over x goes to positive infinity, log of x goes to negative infinity. So overall, this is negative infinity, but that's not the answer. E to the negative infinity, that'll go to 0. Method number 2, change our base formula. And then here, 1 of x is going to positive infinity, log of x is going to negative infinity, so e to the negative infinity, going to 0. And then another problem like this. Yeah, okay, method 1, take the log, take the exponent out, and we have a fraction, so we can use L'Hopital's rule. The answer is negative 1. Oh, did I say the answer is negative 1? Answer to this computation is negative 1, not the answer to the problem. Answer to the problem is e to the negative 1 power. You see, this is the answer to the computation after the log. You have to take the exponential back. Be careful there. And if you use the second method, there's no danger, but the computation here will be a little bit more complicated, longer. Okay, so much for really special, exceptional exponential, L'Hopital's rule problems there. And I admit, I rarely write this kind of problem in the exam. I mean, I used to when I was in engineering university, but nowadays I don't. Ever since I moved to liberal art colleges, I stopped doing this, so don't worry too much about these kind of horrendous computations. Okay, final topic. Avoiding L'Hopital's rule mistakes. What kind of mistakes are there? Failing to apply it properly. Well, we have just derivative, and then going ahead. But this is wrong because L'Hopital's rule works only for fraction. You have to change it to fraction and go ahead. I do see this kind of mistakes sometimes, but those are rare. How about this? Well, this is actually okay, but I've seen some students doing this. I mean, this shouldn't be too much of a problem. As a matter of fact, if you take the derivative twice, the numerator just becomes a constant. But I've seen some students confusing that with quotient rule. Here's how you do it right. But this is not too much of a problem. This mistake is really rare. I've seen that mistake, yes, but really rare. Now this one here, getting warmer, this is going to be a bit more important. Skipping the plug-in step. If you have 0 over 0 type or infinity over infinity type, okay, you can go ahead with L'Hopital's rule. If it is not, then L'Hopital's rule does not work. Like this. L'Hopital's rule does not apply. If you plug in, then you have 4 over 0, that's undefined. But if you try L'Hopital's rule directly, and you get an illusion that you get something. But this is wrong. So if you forget plugging in and checking whether this is 0 over 0 over infinity, then sometimes things can go wrong. Be careful there. Skipping the plug-in step is a big mistake. How about this one here? Well, you can see this is infinity over infinity type, and you can use L'Hopital's rule, yeah, but yeah, it works. But what if you have really large powers so that you have to take the derivative many, many times? Are you going to take the L'Hopital's rule 20 times, really? Much more practical solution is to take the leading terms and then getting their ratio. And then the associate is to horizontal asymptotes. Okay. Finally, the most important. Limits toward infinity with radicals. L'Hopital's rule does not apply here. If you apply L'Hopital's rule, you get correct expression, but it's much harder than before. The purpose of L'Hopital's rule, or any other technique as a matter of fact, is to make this problem simpler so that you can handle. It's getting worse. And this is really, really typical. Limits toward infinity with radicals. Do not use L'Hopital's rule. How do you do that? Well, I hope you guys remember something we did a long time ago in lesson 2, I think. Take the highest degree terms only, and then simplify from there. And then you can cross-check with graphs. That's how you do it. Do not use L'Hopital's rule because the expression is correct, but you cannot calculate it. Of course, you'll see, once you try L'Hopital's rule and the computation is going, oh, this is going with that, and you should be able to come back and ditch L'Hopital's rule and do something else. Here's another example. Infinity minus infinity type limit. You can change the fraction by multiplying the conjugate to both numerator and denominator and then make it into a fraction. And then what do? No L'Hopital's rule, no. Take the highest degree terms and then simplify. You can cross-check with horizontal asymptote. So that's how you can avoid L'Hopital's rule mistakes. And this type, those are rare, so I wouldn't worry too much about it. But plugging in, yeah, that sometimes causes trouble. But most important types of mistakes are these, especially this. If you use L'Hopital's rule, it flat out fails. You get something that is worse than before. Remember, all these are there to simplify the problem so that you can handle. If things are getting worse than before, then you have to abandon and find some other method.